There are different questions one can face in partial derivatives besides determining the derivatives themselves. Check some of them here in differential calculus. One problem is looking for the variables knowing that the function's derivative with respect to x is 0, also with respect to y. The function is 4x squared plus y squared minus 8xy plus 4x plus 6y minus 10. Having the derivatives equated to 0, let's start the first partial derivative of the function with respect to x. F of x is 4 times the derivative of x squared plus y squared times the derivative of 0 minus 8y times the derivative of x plus 4 times the derivative of x, and this continues with 6y times the derivative of 0. And lastly, minus 10 times the derivative of 0. Note that the derivative of x with respect to x is 1. So, f sub x is 4 times 2x multiplied by the derivative of x minus 8y plus 4. So f sub x is 8x minus 8y plus 4. Again, this is equated to 0. Next is to look for f sub y taken as 4x squared times the derivative of 0 plus the derivative of y squared minus 8x times the derivative of y plus 4x times the derivative of 0, then add 6 times the derivative of y minus 10 times the derivative of 0. dy over dy is 1, so the reduced function is 2y times the derivative of y minus 8x plus 6, where dy over dy cancel out again, leaving f sub y as negative 8x plus 2y plus 6. This is also equated as 0. With the two derivatives already figured out, apply simultaneous equations through elimination. That is, with f sub x and f sub y. By adding both equations, we end up with a negative 6y plus 10 equal to 0. And we get y as negative 10 over negative 6, or that is 5 over 3. Knowing the value of y, we substitute this into equation 1, making 8x minus 8 times 5 all over 3 plus 4, and this is also equated to 0. 8x is then 28 over 3, so x is computed as 28 over 24, or that is 7/6. Example 2 is similar with the previous one, with the function x squared plus 4y squared minus 3xy plus 3. With f sub x as 0, we determine f sub x as a derivative of x squared plus y squared times the derivative of 0 minus 3y times the derivative of x plus 3 times the derivative of 0. dx over dx is 1. So the function becomes 2x times the derivative of x minus 3y. Again, dx over dx is 1. So the function turns out as 2x minus 3y. This is equated to 0. Next is to find the equation of f sub y, which is x squared times the derivative of 0 plus 4 times the derivative of y squared minus 3x times the derivative of y plus 3 times the derivative of 0. Here again, dy over dy is 1, reducing the function into 4 times 2y with dy over dy minus 3x. dy over dy cancel out. From here, having the final f sub y as 8y minus 3x. And again, this is equated to 0. With simultaneous equations, this time using substitution, f sub x, which is 2x minus 3y as 0, can be transformed as y equal to 2x over 3. Use this function into f sub y, which is negative 3x plus 8y as 0, to have 7x over 3 equal to 0, where x is also equal to 0. Y is then computed by placing x into the function, where y turns out as 0. Thus, the values of x and y fitting the conditions are 0 and 0. Another problem variation for partial derivatives is shown in the next example. If the given function is xy all upon x squared plus z squared, we are to determine the derivatives with known coordinates -1, 1, and 2. The first requirement is f sub x, and since the function requires quotient rule, the derivative becomes the square of x squared plus z squared in the denominator, and the numerator then becomes the lower term x squared plus z squared times the derivative of xy, minus xy multiplied by the derivative of x squared plus z squared. To act on the derivative, treat y as a constant in the first term, making y times the derivative of x. Then distribute the derivative on the binomial on the second term. After doing this, we reduce dx over dx as 1, and z squared times 0 is 0. The function then transforms to x squared plus z squared multiplied by y, minus xy times 2x with the derivative of x, all over the square of x squared plus z squared. Again, dx over dx is 1, so the partial derivative of the function with respect to x is y times x squared plus z squared, minus 2x squared times y, all over the square of x squared plus z squared. With the required coordinates plugged into the function, we get the partial derivative of f with respect to x as 3 over 25. Moving on to the value of the partial derivative of the function with respect to y. So the function is differentiated similarly as the first one, as it still requires quotient rule. Differentiating it with respect to y, we get x squared plus z squared times x with the derivative of y minus xy times x squared times the derivative of 0 plus z squared times another derivative of 0. And everything is over the square of x squared plus z squared. From the last step, dy over dy becomes 1, and the second term is actually zeroed out. So we are left with the partial derivative of f with respect to y as x times x squared plus z squared, all over the square of x squared plus z squared. Having the final partial derivative, plug the coordinates -1, 1, and 2, giving the value of the partial derivative of the function with respect to y as -5 over 25, reduced to -1 over 5. Another requirement is to take the partial derivative of the function with respect to z, and still the same, we use the quotient rule to initiate the differentiation. With respect to z, we have x squared plus z squared times xy times the derivative of 0, minus xy times x squared times the derivative of 0 plus the derivative of z squared. Both terms are over the square of x squared plus z squared. The first term becomes 0, and what is left is from the second term, negative xy times 2z with the derivative of z over the square of x squared plus z squared. dz over dz is 1, giving the final partial derivative of the function as negative 2xyz over the square of x squared plus z squared. This is the point when we substitute the coordinates into their derivative, and we get the partial derivative of f with respect to z as 4 over 25. The fourth example is similar with the previous one, though this showcases a different set of coordinates. From the function z squared times sine of 2xy, we compute for the first order derivatives of the coordinates 4, pi over 3, and 1. Firstly, we work on f sub x, making the function z squared times the derivative of sine of 2xy. Differentiate it further to arrive at z squared times cosine of 2xy times the derivative of the unit 2xy, which is differentiated again into z squared times cosine of 2xy with 2y multiplied by the derivative of x. At this point, we can equate dx over dx as 1, making the reduced partial derivative as 2yz squared times cosine of 2xy. Using the coordinates, the function becomes 2 times pi over 3 times 1 squared with cosine of 2 times 4 times pi over 3. The trigonometric function is solved in radians to have f sub x as negative pi over 3. Next is to take the partial derivative of the function with respect to y, making the function z squared times cosine of 2xy with the derivative of 2xy. Differentiate this further to get z squared cosine of 2xy times 2x with the derivative of y with respect to y, again taken as 1. Thus, the final partial derivative of the function with respect to y is 2xz squared times cosine of 2xy. Plugging the coordinates again, we make f sub y as 2 times 4 and 1 squared with cosine of 2 times 4 times pi over 3, where cosine is again in radians. F sub y is equal to negative 4. Lastly, solve for the partial derivative of the function with respect to z, where we start with sine of 2xy times the derivative of z squared. After differentiation, the function becomes sine of 2xy times 2z with the derivative of z, where dz over dz is 1, resulting to the partial derivative as 2z times sine of 2xy. With the coordinates, f sub z becomes 2 times 1 times sine of 2 times 4 times pi over 3, where sine is in radians. Then the partial derivative of the function with respect to z is root of 3.